Something impossible happened last night. For 3 hours, 3I/ATLAS, the interstellar comet streaking through our solar system at 61 kilometers per second, vanished. Completely. No light, no heat, no spectral signature. Telescopes worldwide, from the Very Large Telescope in Chile to the Hubble Space Telescope in orbit, lost it. Radio arrays scanning for any whisper of emission heard nothing. Then at 3:17 a.m. UTC, it reappeared. But what came back wasn't the same. The object is now moving at 122 kilometers per second, twice its original speed. No natural comet does that. No known physics allows a 5-kilometer wide chunk of rock and ice to double its velocity in 3 hours without leaving a trail of fire across the sky. The data is clear, cross-checked, undeniable. Something changed 3I/ATLAS, and the implications rewrite everything we thought we knew about interstellar visitors. Let's start with the blackout. At 12:03 a.m. UTC, 3I/ATLAS stopped reflecting light. Optical telescopes, trained on its position, saw only background stars. The James Webb Space Telescope, tracking its mid-infrared signature, registered a sudden drop to baseline noise. No thermal glow, no chemical emissions, nothing. For context, a comet's nucleus, even at 1.8 astronomical units from the sun, emits detectable heat as solar radiation warms its surface. Dust scatters light, gas sublimates, creating a faint coma. These are constants, measurable across wavelengths. But for 3 hours, 3I/ATLAS was a ghost. Ground-based observatories like Gemini South ran immediate diagnostics, ruling out equipment failure. Hubble's wide-field camera 3 confirmed the absence. Radio telescopes, including the Atacama Large Millimeter Array, swept the spectrum for any trace of high-energy processes. Silence. Then, without warning, it returned. Brighter, faster, and chemically altered. The velocity jump is the real anomaly. At its last observation before the blackout, 3I/ATLAS clocked a steady 61 kilometers per second, consistent with its hyperbolic trajectory from interstellar space. Post-reappearance, Doppler shift measurements from the Keck Observatory pegged its speed at 122 kilometers per second. That's not a gradual acceleration from outgassing, like we saw with 1I/Oumuamua in 2017. This was instantaneous, or near enough to defy measurement. To double the speed of a 5-kilometer wide object with a mass estimated at 10 trillion kilograms requires energy on a scale we associate with planetary collisions. The momentum alone, mass times velocity, demands a force that would generate heat, light, or vibrational signatures. Yet during those 3 hours, no telescope caught a flare, no spectrometer saw a spike, no radio dish picked up a pulse. The object simply reappeared, moving twice as fast as if it had rewritten its own physics. What does it take to make a mountain-sized object double its speed? Let's break it down. Momentum is mass times velocity. For 3I/ATLAS, we're talking 10 trillion kilograms moving at 61 kilometers per second before the blackout. To reach 122 kilometers per second, you'd need to impart an additional 6.1 times 10 to the 14th kilogram meters per second of momentum. If this were a chemical rocket, the energy required would be equivalent to burning millions of tons of fuel in a perfectly efficient system. But comets don't carry fuel. They sublimate ice, water, carbon dioxide, methane, when heated by the sun, creating jets that can nudge their trajectory. Those jets produce measurable spectra: water vapor at 2.7 microns, CO2 at 4.3 microns. JWST would see those lines light up. Instead, post-blackout spectra show something new: sharp peaks in the ultraviolet around 250 nanometers and a faint but persistent emission in the radio band at 1.4 gigahertz. These aren't comet signatures. They suggest ionized gas or a process we don't yet understand. The blackout itself demands explanation. A natural comet doesn't just stop emitting light and heat. One theory floating among astronomers is a catastrophic shadowing event. Imagine a massive dust cloud ejected from the nucleus, temporarily blocking sunlight and cooling the surface. But dust clouds don't form instantly, and they don't dissipate in 3 hours without leaving a trace. Another possibility is a physical obstruction. Perhaps the comet rotated, presenting a low albedo, non-emissive face to our telescopes. But that wouldn't explain the velocity jump, and Hubble's photometry would have caught subtle brightness variations before the blackout. A third hypothesis, whispered in observatory control rooms, is more radical. The object entered a state where it absorbed or redirected all emissions. No known material does this naturally, but engineered systems, like stealth technology scaled to astronomical proportions, could theoretically mask a signal. The catch? That requires intent, design, something beyond ice and rock. The instruments are working overtime now. The Very Large Telescope in Chile is running high-resolution spectroscopy, hunting for chemical clues in the post-blackout emissions. JWST's near-infrared spectrograph is mapping the nucleus, looking for surface changes that might explain the ultraviolet spike. Radio telescopes, including the Green Bank Observatory, are locked onto that 1.4 gigahertz signal, searching for patterns or modulation that might suggest structure, not noise. Mars orbiters, positioned 29 million kilometers from 3I/ATLAS's closest approach in early October, are reorienting to capture high-resolution images from angles Earth can't match. Juno, orbiting Jupiter, will get its shot in March, offering parallax data to confirm the new velocity with precision. Every observatory is synchronized, cross-referencing, waiting for the next anomaly to confirm or debunk what we're seeing. Let's talk about the stakes. If 3I/ATLAS doubled its speed through a natural process, we're witnessing a phenomenon that rewrites cometary physics. Maybe it's a new kind of volatile, a subsurface reservoir of hyper-efficient fuel that ignites under specific conditions. That alone would reshape our models of interstellar objects, suggesting they carry energy sources we've never imagined. But if the speed change was controlled, deliberate, precise, it's a game changer. Propulsion without visible exhaust, acceleration without thermal bloom, implies technology beyond our current understanding. The energy requirements for such a maneuver are staggering, yet the blackout suggests efficiency we can't replicate. If this is artificial, the implications cascade. Navigation, energy production, even our approach to interstellar travel would need to be rethought overnight. What could cause this? Let's explore the natural explanations first. A massive outgassing event could, in theory, boost velocity. But to double it? You'd need a jet of material ejected at speeds far exceeding anything we've seen in comets. The mass loss would be catastrophic, tens of percent of the nucleus, leaving a visible coma and tail. Yet post-blackout images show a tighter, more compact coma than before, as if the object stabilized after the event. Another possibility is a collision. A high-speed impact with a smaller body could impart momentum, but it would also generate heat, debris, and spectral chaos. No such signatures appeared. The most speculative natural theory involves magnetic interactions. If 3I/ATLAS carries a significant magnetic field, it could interact with the solar wind, gaining a boost. But the solar wind's energy density is orders of magnitude too weak to move a 10 trillion kilogram object this fast. Now, the artificial hypothesis. If 3I/ATLAS is a constructed object, the blackout and velocity jump suggest a maneuver. Controlled propulsion would leave signatures, directional emissions, thermal spikes from energy release, or radio bursts from onboard systems. The 1.4 gigahertz signal is intriguing. It's a frequency associated with neutral hydrogen in nature, but also a band used in terrestrial communication. If it's modulated, repeating with mathematical precision, it's a flag no astronomer can ignore. The ultraviolet spike could indicate plasma exhaust or a high-energy process, not unlike ion thrusters scaled to unimaginable size. The blackout itself might be a stealth mode, absorbing or redirecting emissions to avoid detection. These are speculative leaps, but they're grounded in what we're seeing. An object that defies natural behavior and demands we consider every possibility. The global response is immediate. Observation schedules have shifted. The Vera Rubin Observatory, still in its commissioning phase, is prioritizing 3I/ATLAS for its wide-field scans. NASA's Planetary Defense Coordination Office, typically focused on near-Earth asteroids, is now modeling the object's trajectory to rule out any risk, however remote. ESA's Comet interceptor mission, designed for rapid response to transient objects, is being reevaluated for a potential launch window. SpaceX and Blue Origin, always quick to seize opportunity, are quietly discussing fast-track intercept concepts, small, agile probes that could reach 3I/ATLAS before it exits the solar system. The timeline is tight. At 122 kilometers per second, it's on a one-way ticket out, and our window to act is closing. Imagine that intercept mission. A lightweight spacecraft, built from off-the-shelf components, launched on a high-energy trajectory. A SpaceX Falcon Heavy or ESA Ariane 6 could loft it, using a solar gravity assist to slingshot toward the comet. The payload is simple: high-resolution cameras, a thermal imager, a mass spectrometer. Fly by at 100,000 kilometers, close enough to map the nucleus, measure its composition, and detect any artificial structures. If the surface shows geometric patterns, vents with unnatural precision, or materials that don't match known cometary chemistry, we'd have our answer. The mission could launch in months, not years, if the anomaly holds. It's the kind of bold move that defines eras, the moment we stop observing and start chasing. What does this mean for us? If 3I/ATLAS is natural, we're on the cusp of discovering a new class of interstellar objects, ones with volatile dynamics we've never modeled. That's a scientific windfall, reshaping our understanding of how planetary systems form and eject material. But if it's artificial, the consequences are existential. Proof of controlled propulsion would force us to rethink our place in the cosmos. We'd need to listen harder, scanning for signals across every wavelength. We'd need to build faster, developing interceptors to meet these objects on their terms. And we'd need to talk, globally, urgently, about how to respond when something moves with intent. The economic upside is massive. New propulsion technologies could unlock deep space. The security risks are equally real. Detection protocols, international agreements, and response frameworks would need to be in place yesterday. Let's zoom into the physics. A 5-kilometer object moving at 122 kilometers per second carries kinetic energy on the order of 10 to the 20 joules. To achieve that speed increase in 3 hours, you'd need continuous acceleration at roughly 0.005 meters per second squared. For a 10 trillion kilogram mass, that's a force of 5 times 10 to the 13th newtons. No chemical rocket scales to that level without a visible exhaust plume stretching thousands of kilometers. Even advanced propulsion, ion thrusters, nuclear pulse, would emit detectable heat or radiation. The absence of those signatures during the blackout points to an energy transfer we don't understand. The ultraviolet and radio emissions post-blackout are our only clues, suggesting a process that's either hyper-efficient or deliberately masked. The origin story of 3I/ATLAS adds context. Interstellar objects are born in chaotic systems, young stars with crowded planets, where gravitational slingshots eject debris at high speeds. A 61 kilometer per second exit velocity fits that model. A Jupiter-sized planet flinging a comet out of its orbit. But doubling that speed requires an onboard energy source or an external interaction we haven't modeled. The chemistry offers hints. Pre-blackout spectra showed typical cometary markers: water, CO2, some silicates. Post-blackout, we're seeing those ultraviolet lines and a metallic signature, possibly ionized iron or nickel, not typical in comets. This suggests a denser processed core, perhaps forged in a violent stellar environment or altered by something else entirely. We're not guessing blindly. The tools are in place. Mars orbiters will image the nucleus in October, resolving details down to 50 meters. Juno's March flyby will pin down velocity and trajectory with parallax precision. Ground telescopes are tracking light curves, looking for spin changes that might indicate asymmetric thrust. Radio arrays are dissecting that 1.4 gigahertz signal, hunting for repetition or structure. If 3I/ATLAS maneuvers again, we'll see it in real time. Light curves will shift, spectra will spike, and the data will converge. If it stays quiet, we'll still learn something profound about what interstellar objects can do. The human element can't be ignored. Scientists are working around the clock, fueled by equal parts excitement and unease. Observatories are sharing data faster than ever, with global networks coordinating in real time. Space agencies are dusting off contingency plans, asking what it would take to chase this object before it's gone. The public is watching too. Posts on X are exploding with theories, from natural phenomena to wild speculation about alien probes. The truth, as always, lies in the data. But the questions we're asking now, about propulsion, intent, and our readiness, will shape the future regardless of the answer. This is where we stand. An interstellar object went dark for 3 hours and came back moving twice as fast. The signatures don't match any known comet. The energy scales defy natural processes. Every instrument we have is trained on 3I/ATLAS, waiting for the next clue. If it's natural, we're about to rewrite cometary science. If it's not, we're staring at a discovery that changes everything. So I'll ask you, if we confirm this object moved on purpose, what's our next step? Do we chase it? Do we listen? Do we prepare for what comes next? Drop your thoughts below, because the choice we make now might define the next century.